So let's bring in the merry-go-round from Friday, and all the same parameters for it. So it's got a radius of 2 meters and a mass of 150 kilograms, and we'll treat it as a disc. But this time, what I'd like to do is talk about how we might get the merry-go-round to get up to speed. And one way to do that is to have a kid run at the edge of the merry-go-round. Can you imagine what this kid might do to try and get the merry-go-round to spin? So they run towards the edge, and when they get there, jump on, and then the kid and the merry-go-round go spinning around. Okay. Clearly, the merry-go-round acquires angular momentum from the kid. But the kid has linear momentum here, which is going to be converted to some form of angular momentum for the merry-go-round and the child. Now, I said to you before that linear momentum and angular momentum are different units. They measure different things. And I'm sticking by that. I'm not changing that. In fact, in this question, the linear momentum of the child becomes 0 after they jump onto the merry-go-round. But that's because there's an external force on the system. The merry-go-round is attached to the ground. Because it's attached to the ground, when a kid jumps onto the merry-go-round, they probably apply a force this way to the merry-go-round, right? Their feet and their body hitting the bar and grabbing onto it, push on the merry-go-round in that direction. But there's a force from the ground on the merry-go-round in this direction, right, where it's mounted to the ground. So although there are two forces acting here, one on the merry-go-round and one on the child, those two forces act at different places on the merry-go-round. So while the merry-go-round, while the merry-go-round doesn't change location, because these two forces cancel out, that doesn't mean the merry-go-round won't spin. This force keeps the merry-go-round from going someplace, but this force from the child on the merry-go-round is acting not at the center, but at the edge. So the merry-go-round acquires a spin, even though it doesn't change location. Now the kid experiences just the one force. The kid is experiencing a force this way from the merry-go-round. That stops the kid from changing location because they are now attached to the merry-go-round. So the kid loses linear momentum, but the system retains angular momentum. Everybody understand that argument? So the force I drew in the middle, there's the force of the kid on the merry-go-round. That'd be like there. But there's the force from the ground on the merry-go-round as well. This force doesn't cause a torque because it acts at the pivot point. This force causes a torque because it acts away from the pivot point. Now, from a problem-solving point of view, using force here would be tough. We probably don't know the size of the force, and even though we know where it's applied, it might be difficult for us to figure out how fast the merry-go-round is traveling after the kid jumps on, because we have no easy way of knowing how much force there was and for how long the force was applied before the kid came to rest relative to the merry-go-round. Those variables don't exist. But like other collision questions, we really weren't interested in dealing with the forces of a collision. We were interested in finding a way to solve for what the resulting velocity was after the collision. So there's a way to do that here. And in fact, there's a way to describe the kid's angular momentum before the collision. Even though he's a point mass and he's traveling in a straight line, we can define something called the point mass angular momentum. Now, the kid doesn't really have angular momentum. The kid is not spinning around. Nothing like that's happening. But we know that the future of this problem is that the kid's going to be jumping onto the merry-go-round, and that's going to cause the merry-go-round to spin. From the vantage point of the merry-go-round, it can be said that the kid does have angular momentum relative to the merry-go-round. Consider if you were standing at the pivot point of the merry-go-round, and I connected a line to where the kid is. Can you guys see that red line? As the kid travels in the straight line, let's say they don't jump on the merry-go-round, they just pass right by it. If you're on the merry-go-round and you're watching the kid, you would have to see him pass by you as if you was turning your head to follow him, right? That means relative to the axis of the merry-go-round, the kid can be perceived as rotating around the merry-go-round, even though they're actually just going in a straight line. Because from the vantage point of where you're standing, you would have to pivot to track them. Does that make sense? That's how we define the angular momentum of a person traveling in a straight line or an object traveling in a straight line. They don't have angular momentum per se. They have angular momentum relative to a fixed point. Okay, so they don't have angular momentum per se. They have angular momentum relative to a fixed point. Now, if the kid was just running in a straight line and never jumps on the merry-go-round, that idea of his angular momentum doesn't make sense. It doesn't make sense out of the context. His angular momentum only makes sense in the context of him jumping on the merry-go-round, right? Because it's going to cause the merry-go-round to spin. So although if I'm just running in a straight line, there's multiple points of reference all around me, but I would not say that I have angular momentum because none of that's useful. I'm not jumping on any of those objects. But if at the end, there's a result where the kid does jump onto the merry-go-round, well, suddenly the merry-go-round becomes the point of reference because there's going to be a rotation of the merry-go-round after the kid jumps on it. So when we talk about this idea of an angular momentum for an object traveling in a straight line, it's only valid in a context where there's some resulting spin afterwards. We're going to see several examples of this, but consider something like this. You guys may not play golf, I don't, but you probably understand that a golf ball gets hit by a club, and the person who's holding the golf club rotates their body, right, on their way to striking the club. Well, they have rotational momentum. When they strike the ball is going to have linear momentum, but we can perceive of the ball having angular momentum relative to the axis of rotation of the golfer. That's how we can figure out how fast the golf ball must be hit from the rotating golfer. Well, it's the same problem we're talking about here, but in reverse, right? What if the kid was on the merry-go-round and gets flung off? We could describe the change in velocity of the merry-go-round and the kid based on conservation of angular momentum. So all of these are angular momentum collision style problems. We're going to look at all of them. Now, the way we calculate point mass angular momentum for an object traveling in a straight line is going to look kind of silly. We use a lowercase l, and that's the best I can do because if I make just a line, it looks too much like a 1. So from now on, this lowercase l or script L is supposed to represent angular momentum because it's still an L, but I'm using the lowercase to signify that it is a point mass traveling in a straight line. And the calculation for it is R cross P, where R represents the vector from the axis of rotation to the point mass. And P represents the linear momentum of the point mass. Now, I need to emphasize it's cross product, which means our result is also a vector. So just like angular momentum before, angular momentum has direction. And the cross product is always in an order to help you figure out the direction of the angular momentum. It's R cross P. Remember our three finger rule for cross products? Pointer finger is the first vector, middle finger is the second vector, and your thumb is the direction. So I point from the axis of rotation towards the object, that's R. I align P with the direction of the momentum, which is, I know I have to put my finger back a little ways, but remember, it's anything over here would still result in the same direction of momentum out of the board. So the kid has a direction of momentum that is out of the board, which makes sense because we expect this to spin later in this direction. Doesn't it make sense that the momentum for this spin is still out of the board? So now do you understand why we use the cross product? It's to help us determine the direction of the angular momentum, and that it has to be in full agreement with the direction of our momentum of the merry-go-round after the kid jumps on it. All fair enough? Straightforward enough for you guys? Well, it's a cross product. If you remember, a cross product's value is the value of r times the value of p times the sine of the angle between them. So we're talking about this angle. Now, this part might be challenging for you to understand, so I want you to think about this for just a second. Does r stay the same very long? No. In fact, this might kind of freak you out a little bit. If the kid's running at a constant speed, so their momentum isn't changing, that's great. So this isn't changing, but r is certainly becoming a smaller and smaller number, isn't it? In fact, where we are now, r clearly smaller here. So this is r1, this would be r2. r2 is clearly smaller than r1, right? But phi is getting bigger, right? The question is, if he's running at a constant speed, shouldn't the angular momentum be constant? It wouldn't make any sense for it to be a changing value, because then how would we deal with the fact that the angular momentum is changing all the time? And I'm here to tell you that r gets smaller in the same proportion as sine phi gets bigger. We can prove it. So I'd like to prove it to you just so you've seen why that has to be true. Is that okay with you guys? I hope so, because what else are you going to do? Say no? All right, I'm just going to move it a little bit to line it up flat. Is that okay with you guys? See what I've done? I'm going to take and draw a triangle right here. Can we all agree that this side is R1, and then it's the hypotenuse of that right triangle? This would have to be phi1 as well. This side is the opposite side of phi. Would you agree? And would you agree with me that that's got to be R1 sine phi1? Doesn't that have to be true? Sine is opposite over hypotenuse. All good? Any question about where that came from? So I think this is overkill, but let's go ahead and do it. Let's draw the other triangle here. Wouldn't this have to be R2? And wouldn't this have to be phi2? Right? Is it pretty clear that that's still got to be the same opposite side? So in this circumstance, the opposite side is R2 sine phi2, but they equal the same thing. Does that prove to you now that R is changing in the same proportion as sine phi is changing? So it's a constant. In fact, it is sometimes written that this is R perpendicular times P. R perpendicular would be this opposite side, the point of closest approach, right here. Right, that's R perpendicular. That's when they are closest to the axis of rotation. So most of the time in a problem like this, we wouldn't actually say where the kid starts. Right? Although we're going to calculate the angular momentum, we only care about the angular momentum because the kid is jumping onto the merry-go-round. So I wouldn't tell you where the kid starts. I would just tell you that the merry-go-round has a radius of 2 meters. Right? If the kid keeps the same speed, we know what their momentum is going to be just before they hit the merry-go-round. That's all we need. So oftentimes, we'll never know where the kid starts and what R is. All we'll know is what the instantaneous moment is just before the collision, where the kid is right there at the closest approach. All good? So let's talk about this question specifically. We'll do this one all the way through. So I'm going to take all these triangles off now, and let's kind of clean this up and talk about the answer to this problem. I want to find out how fast is the merry-go-round going after the kid jumps onto it. Okay? So the kid runs, jumps on the merry-go-round. Let's say this kid is the same kid as last week, so they had a mass of 30 kilograms, and let's say they're running at a nice brisk pace of 2 meters per second. Let's find the angular speed of the merry-go-round after the kid jumps on it. Like any collision question, we're going to have a before and after. So the only thing with angular momentum before is the kid. And since the kid becomes part of the system, the only thing with angular momentum after is the merry-go-round with the kid on it. All good so far? Now to calculate the calculate the angular momentum of the kid, we're going to use the point of closest approach, meaning I'm not going to say r times p times the sine of some angle. It's not what I'm going to do. I'm going to say r perpendicular times p, because at r perpendicular, the angle is 90 degrees. And that's going to equal, well, the moment of inertia of the merry-go-round plus the moment of inertia of the kid times omega. I'm just setting the problem up because I'm only going to do calculations for this one. After this, we're just going to set problems up so we can kind of see what they're going to look like. Is that good for you guys? Let's go and work this one through a little bit, though. When I say r perpendicular, we are talking about where the kid jumps on the merry-go-round. So for this problem, that's going to be the kid jumping right on at the edge. That's assuming he jumps on at the edge. If he jumped on somewhere else, this would be different. But if he jumps on at the edge, that's 2 meters away from the axis of rotation. Agreed? So I'm going to have 2 times the kid's momentum, which is 30, times its speed, 2 meters per second. This is meters, kilograms, and meters per second. This has to equal, well, we're going to need the moment of inertia of the merry-go-round. Do you guys remember it from Friday? 300. It's a disk of mass 150 kilograms and radius of 2. So I'm going to use 1/2 mr squared. And that's going to be 300 kilograms meters squared. The kid's a point mass. Do you know how to calculate the moment of inertia of a point mass? mx squared, right? So the kid, 30 kilograms, 2 meters away from the edge, right? Their point mass is at the edge of the merry-go-round times omega. So 30 times 4, 120, 120 plus 300, 420. So 420 kilograms meters squared times omega. And let's see, 20 times 30 is 60, times 20 is 120. This is 120 kilograms meters squared per second. All good? Any questions about any of that? All right. The answer's not that big a deal, 120 divided by 420. But pay attention to the units. So when I divide this out, I'll get 120 divided by 420, but my units, the kilogram meter squared will cancel out the kilogram meter squared there. So I'm left with units of apparently nothing per second. When you're working out a problem that has to do with rotation, and your units work out to be nothings per second, what goes up there? Radians. That's right. This is radians, not rotations, not revolutions. It's radians per second. Radian is a unitless quantity. So when you work a unit out and it comes out to be nothing, when you're dealing with spin, that's going to be radians. We all good? All right. Last week when we talked about this, we talked about they weren't collisions, but they were conservation of momentum problems. We talked about the kids walking towards the center, and that's spinning up the ride. And what I said to you is something you need to remember is that work was being done when the kids walked to the center, because the energy afterwards is greater than the energy before. Do you think the energy here is greater than the energy before in this collision? We could just test it, right? Well, let's not assume. Let's go ahead and test it real quick, because I'm not convinced. This looks like a collision where there was an external force that took away momentum. I think there's less energy afterwards, but we don't have to guess. We can check. So the kid has 1/2 times 30 times 2 squared joules of energy, right? Mass times velocity squared. So that looks like 60 joules of energy, if I'm doing my math correctly. Now, you'll need your calculator for this. The merry-go-round, 1/2 times I times omega I know what I get. Whole lot less, right? Mm-hmm. I got 17 joules. What'd you guys get? So, no, the energy is not the same. Now, the kid could walk towards the center. That might increase the energy, but that would come from the kid. In this collision, energy was lost, right? Just the collision portion, energy was lost. There was an external force in the system that took away energy from the system. We all good? All right. I want to show you a bunch of variations on these kinds of problems. So let's look at the first variation. Someday I'm going to set this back up. I used to have a system I could do this with, but right now I can't. But eventually I'll use my Airtable to set this example up. All right, so imagine I have two objects that are going to be involved in a collision. And I've wrapped something like Velcro on both sides, the opposite kinds of Velcro, so when they come together, they'll stick together. Fair enough? If I fire that sucker off and fire that sucker off and say they both have the same mass and they're fired at the same velocity, right at each other, what would be the total momentum of this system? Be zero. That's right. Momentum has direction. And so I have mv to the right and mv to the left. They will add up to be zero. So when they strike each other, the momentum of the system will have to be zero. They're going to stick together. That means that when they strike each other, they're going to stay in place. Right? Not a big deal. Simple enough problem from first semester. Us talking about these kinds of collisions. Well, so if I set them slightly offset like this, or maybe perfectly offset so they just connect at their edges, what's the momentum of this system before the collision? The linear momentum is zero, but the angular momentum is non-zero. These two don't have opposite angular momentums. Consider the direction of the angular momentum. Now, to do that, you have to imagine that there's a point in between these two objects where they stick together. Can you imagine that point? Now, if you're thinking about that point, let's say that that point is here, in the center. when they stick together, they're likely to rotate about that point. So currently, R for this puck would be going this way, so it would have a rotation like that, right? And for this puck, which is going this way, it has a rotation like that. So can we see that they both have the same direction, angular momentum? So this has got 0 linear momentum, but has angular momentum. In fact, the two disks will make it all the way to the point where they touch, say right here. And when they do, they're going to have become one object with some kind of combined moment of inertia that's going to spin here. Now, ice skaters do this all the time in couple skating, right? They come at each other from different angles, and then they grapple and they spin. Same idea here. So in this problem, if you're trying to calculate the angular momentum, I think we have an angular momentum of puck number 1 and an angular momentum of puck number 2. They'll be the same. You just have to double it, assuming they have the same mass and same velocity. Together, they will form one object with a combined angular momentum L. So something like this. Straightforward enough for you guys? There's a few things here I hope that you realize. The point of closest approach would be the radius of the puck. Do you guys see that? Wouldn't that have to be true? Because they're going to touch right about their edges. So the closest approach would be that radius. So I'd say that their angular momentum would look something like that. Probably times 2, because they're both in the same direction. The thing I have to be careful about, let's say the puck is a disc. When they join together, they'll have a moment of inertia, but it's not about the center of the disc, is it? So I'd have to use probably the parallel axis theorem to get the moment of inertia about the edge of a disc. And there are 2 of them, so I'd have to multiply by 2 to get the total moment of inertia of the system. And then omega. Make sense? Question about that? All right.
You said we use the parallel axis theorem twice because we're trying to find the moment of inertia at the end of the disk.
Well, there's 2 discs.
Yeah.
So they're going to be, each disc is being spun about its outside edge. So I'm using the parallel axis theorem on one disc, but then multiplying it by 2 because there's 2 discs that are spinning. Does that make sense? Let's look at another example. Let's say I have a same air table, so some kind of frictionless surface. And I have a rod on that surface. Let's say the rod has a pivot point that is right at the end. And I have the same puck as before. And it's going to have a velocity towards the rod. There's a couple different ways to see this kind of problem. You have a question?
Yeah. Going back to the last
Now, if the puck sticks to the rod, do you see that this is the same as the kid jumping on the merry-go-round? Does that make sense? You know, we just have the moment of inertia of a rod and a point mass that sticks to it. There's one distinct difference here, though, and that is in the merry-go-round question, we had the kid jump on the edge of the merry-go-round. But this object can literally be aimed anywhere, right? And the truth is, I was being a little bit practiced there. I don't have to have it strike something perfectly perpendicular. So in And a problem, if they hit at an angle, you will have to take the angle that they hit the object at into account in your calculations. So keep that in mind. But the big thing too here is, you note that there's no angular momentum if I fire this right at the center. Does that make sense? Just like if the kid ran at the center of the merry-go-round and jumped on it, would the merry-go-round spin? No. But don't just assume that you'll get the maximum rotation if you go right at the end. Don't assume it, because I want you to think about it. If you hit at the end, you're also creating a larger moment of inertia after the collision. So if your goal is to try and maximize the speed of the rod after this collision, well, where you strike it might matter. And you could probably prove where that point is, because you guys know about optimizing for mathematics, right? That there's a way to determine optimization. So if you want to optimize for a higher speed, there's ways that you can check your math to optimize. Now, if you haven't heard about the phrase optimizing yet, don't worry, it's coming in your future, very likely. Now, I do want to also point out a few other things. What if, instead of sticking to, the object bounces off? So say we have something like this. Now this is getting to the point where we're talking about a bat striking a ball kind of thing. Right now the plank is at rest, but you can imagine where the plank might have an angular speed before the collision. You have a question?
Yeah, I mean, it's basically about that. With the previous example, what would we do if the two balls weren't stick together?
If they weren't,
Yeah, if they don't stick together.
then nothing happens. They just pass by each other.
Of course.
Now, if they were enough to touch,
Yeah, that's-
then you might get a two-dimensional collision.
Okay.
The momentum of the after the collision would still have to be zero, which suggests they'd probably go off at equal angles in different directions.
But then would both of them also still have a component of rotational momentum?
You mean like they touch and it makes them individually spin? That's plausible. But now we're getting into a more complicated territory. Probably not going to be part of our scope, but you're touching on a problem that would be part of our scope. So let me see if I can't get to it, okay? I don't want to set up a bunch of these different examples, but do you see, like in this example, if we set the angular direction, in this case, I'm thinking of an angular direction where the plank's at rest at the start and the disc sets the direction for positive as being counterclockwise. You guys following that idea? That we're starting here, so the direction of this angular momentum is out of the board. All okay with that? You follow what I'm trying to say? Because the recoil of the ball would be the opposite direction, right? So that would suggest that if we're looking at the direction out of the board being made positive, this would have to equal something that's probably going to be negative plus the angular momentum of the rod if it bounces off. Now, that's not a surprise. When we did this problem a month ago or 2 months ago and had a ball strike something and bounce off the wall, remember, after the collision, the velocity was negative because we picked a direction for the momentum, and usually the starting velocity was positive, so a recoil would be negative. Same thing here. If you want, you can just say that this is going to be R perpendicular MV, and when it bounces off, you'll have some negative velocity here. All okay? Any questions about this yet? Okay, so let's make this a little spicier, if you don't mind. During the collision, there was an external force on the rod. It occurred at the pivot. So it didn't cause a torque, but it made sure the rod stayed in place. which is why the linear momentum isn't conserved. But if Okay, so same rod, same frictionless surface, puck. But this time we don't fix the rod in place. No pivot point. Right? No external force on the rod. Here, take away the pivot point and the ball strikes the rod, there's no external force on the system. So in this circumstance, linear momentum and angular momentum will both be conserved. Everybody okay so far? There's a whole bunch of things you have to think about under this circumstance. First, whatever the linear momentum of the ball is, that will determine the linear momentum of the system. Now, angular momentum is going to be a little more complicated. Yes?
I have a question. So, in this example, are we considering that like there is no pivot point, as in it's just like in space, like?
I didn't nail it down.
Okay. Okay.
The other one I nailed in place.
Okay. And this one is just like. Static.
I'm saying it's just resting on a frictionless surface.
Okay.
So the first question that we have to probably produce is, if the ball sticks or whether it bounces off makes a huge difference on how this problem will behave, a bigger difference than before. Part of the reason is because objects that have no fixed point of rotation will rotate about their center of mass. So let's say the puck bounces off, as our example here. If the puck bounces off, then after the collision, the puck will have linear momentum because it bounced off. And the rod will have motion about its center of mass because momentum has to be conserved. But also, the rod is likely to be spinning now because the puck strikes it somewhere offset. It's going to spin about its center of mass. So it will begin rotating and begin moving off to the right. Angular momentum has to be conserved and linear momentum has to be conserved. So before the collision, I have P for just the puck. After the collision, I'll have P for the puck plus P for the rod. Before the collision, I'll have angular momentum for the puck. After the collision, I'll have angular momentum for the puck plus angular momentum of the rod. All okay? Still following this all right? Now, here's where it might get a little bit more complicated. What if instead the puck sticks to the rod? The only thing that you really have to worry about here is this system still conserves linear momentum, but there's only one object now. So one object with a combined mass, right? So that would be a perfectly inelastic collision. But the system's going to rotate about the center of mass of the system. Well, that's probably not the center of mass of the rod any longer, right? If the puck sticks to the rod, the center of mass of the system has probably changed. This part's important. Please write it down. I know. But I don't want to lose this moment. You have to know to calculate the center of mass before the collision, because that determines the angular momentum, right? The point of closest approach is going to be based on where the center of mass of the system is, because that's the closest approach, because that's the pivot point. In both of these problems, the pivot point still dictates how we calculate the angular momentum of the puck. So in the first one, it was just, we calculate it from the center of the rod because they don't stick together. But this one, we have to calculate the center of mass as if they stick together and then use that distance to figure out what R perpendicular is.